or it is a mistake? I think it is a mistake. You have raised your hand. So we have seen also that there are some disadvantages of Newton's method, and we have mentioned that we can modify that Hessian matrix. Hessian matrix has to be positive definite. If it is positive semi-definite, then what will happen? That means at least one of the eigenvalue is 0. Then we have seen that the method is actually divergent. It does not give the solution. Okay, so let us just recall and see one example. So the target is to find the minimum point. And the iterative formula for Newton's method is this one. F, we can call it a Hessian matrix, inverse Hessian matrix, inverse of the Hessian matrix. And G is the gradient at that point. So with this formula, we have seen that if a function of fourth order function is given, we have seen for quadratic function, if the degree is 2, then Newton method converges within one iteration. Okay, but if the degree is not 2, here we have x to the power 4. So it is not quadratic, the non-quadratic formula. So if we try to solve this, so let us perform some 3 iterations. We'll calculate this, the gradient, and then try to find out the Hessian. Okay, and the initial point that is given, we'll evaluate at x naught. X naught also we will evaluate x naught value here. Then the gradient becomes this form, and the Hessian matrix f of x naught becomes this one. Now, if we want to try to find out the inverse, just you can use Excel or MATLAB, just a simple function, because hand calculation is difficult in this case, 4 by 4 matrix. So we have to use some computing tools. So let us find out the inverse, and we will try to find out the first iteration, that is the x1 point. The next for iteration 1, we perform this all these calculations, all these computations are done. Now we can see that f of x1 is actually 31.8. Initially what we had, f of x naught is actually 215. So we are actually gradually, so this is 200 to 15. So this is nothing but f of x naught. So yes, we are going in the right direction. That means as x1, x naught, x1, I mean, as the index will increase, that means the function value actually decreases. So we are going in the right direction. Okay. Now, right now we have x1 value of this form. Okay. So again, from this, we will try to find out the next iteration x2. Okay. We'll repeat the process because the gradient we have already calculated. gradient of f. So at x1, we'll evaluate the gradient. Similarly, we'll evaluate the Hessian matrix at x point, x1 point, and then we try to find out the inverse, and we multiply with g1, and finally we'll actually matrix multiplication we'll do it. So after that we'll try to find out this x2 minus x2 equals to x1 minus of this form. So again we are actually getting some better value, so 31.8. so this is okay, so this is f of x1. So we are going in the right direction because f of x2 is less than f of x1. So similarly, iteration 3 if we perform, so we'll calculate the gradient at x2, the Hessian matrix, and then the inverse Hessian matrix, and we'll multiply with the gradient value. So again we are seeing that this is a decrease 6. So we can see that we are gradually converging to the optimal point. Okay. Now in this way we actually perform, provided this Hessian matrix is positive definite. If it is not positive definite, then we will have trouble. Okay. So these are the remarks that has been made for. Now if this second order derivative is negative, then Newton's method fails to converge to the minimizer. Okay. So this is for one variable case also. Similarly, for several variable case also we have the same situation.
0 or negative?
Negative, negative, not 0. Negative definite or 0 also for both cases.
Sir, if function will be positive definite also then.
No, this is the second derivative. What is Hessian? Hessian is the double derivatives, right?
Yes, sir.
Del to f. Okay, this is for single variable case. X is a single variable. Okay. fxx, fxy, fyx, and then fyy. Take this. If the double derivative is negative, then this is not a positive definite. For positive definite, what we have to say? This one fxx is greater than 0, and the determinant is also greater than 0. Then we say this is a positive definite. But if the double derivative or the second order derivative is one of them is negative, then it is not anymore actually positive definite. Okay. So this modification we have to make. If we have a negative definite or at least semi-definite, at least one of the eigenvalue is 0, then what we have to do is we need to write in place of this Hessian matrix. Earlier we had Hessian matrix f of xk inverse. So in place of this, we will substitute some mu k into I, so that the resultant matrix becomes positive definite. How we can make it? We will see. If the value of mu is, for example, 10 to the power 4. Okay, for example, let us say If you remember, one of the Hessian matrix we had 4, 2, 2 and 2. Now if we substitute 10 to the power 4 into, this is identity matrix 1 0 0 1. So what it will be? So 4 plus 4 2 2 2 plus, so this is 10 to the power 4 0 0 10 to the power 4. So the resultant matrix becomes, if you think about, 1 0 0 4, then 2, sorry, 0 4, okay, and 2 1 0 0 0 4. Okay, so this becomes the matrix. Now if you try to find out the inverse, what will be the inverse of this matrix? No, this is 2 is there, so this would be 2. Okay, so inverse of this matrix is actually, let me write down. This will be actually, if you calculate this one, yeah, this one. Now, if you remember the eigenvalues of diagonal matrix, so lambda 1 0 0 lambda 2. Remember the diagonal matrix, eigenvalues are nothing but the diagonal elements. Now, because of this operation, so this matrix has become, this inverse of this matrix has become of this form actually. So this is a very small amount, or both of them are positive quantity in the diagonal, this diagonal positive, this diagonal positive. But if you look at other points, so these are very, very small, almost compared to 0. These are also compared to 0. So that means this particular matrix is actually converged to a positive definite matrix. So this is the main idea of this Levenberg modification of this method, of Newton's method. Okay. Now we will try to look at one example, so that this is a theoretical proof that if we have lambda 1, lambda 2 and lambda n, are eigenvalues of f, then what happens? By the definition, fx equals to lambda 1 into, let us write lambda I equals to 1 to n. So this will be satisfied. F means our f of x actually, the Hessian matrix at that point, at particular point. And this x is actually the vector. This is a vector. Okay. Now, if we try to sum up, by definition, what we are doing is actually g of, let us write v vector, another different vector v. So g equals to, we are calling it f of mu into I into v. So let us see that f of v, f into v plus mu I of v is equals to v, mu into v, because identity into another vector is nothing but the another vector. Okay. So for f of v, we can write this is lambda I into v plus mu plus v. So if you take v outside, so this is we are getting gv equals to lambda I plus mu into v, which means lambda I plus mu is eigenvalue of g. So that is what we have mentioned. And we have to make this mu large so that this matrix becomes positive, all the eigenvalues becomes positive, so that we can get the positive definite matrix. The modification, that target of this modification, I mean the aim of this modification is to make this matrix as positive definite. So this is what actually done. Now, for it has been proved that for sufficiently large mu value, if we take sufficiently large mu value, then the direction is actually descent direction. The gradient descent direction we have seen, although it has some, remember we have seen that minus delta f of x, that is the direction. So similarly, this direction, this particular direction will become one descent direction with this modification. Okay. Now, normally what we do is actually x equals to xi plus 1, xi plus lambda I into sub delta lambda I into si, this direction plus step length. Okay. But for this method, we do not need to use this actually, this step length, although we can define, but for that we have to again calculate this lambda I value. This is one benefit, that we don't have to calculate this lambda I explicitly, because for we have seen for lambda I we have to evaluate f of lambda, okay, and then we have to do this delta d lambda df d lambda, we make 0, then try to find out the lambda star. So this is one extra calculation we have to do. But for this method, this particular modification, we do not need to use this lambda value. Anyway, we can also introduce, but we have to look at the situation that every time we go for next iteration, the functional value will be less than the previous functional value. Okay. Now, if you just try to look at one example, okay, so this is actually a brief idea that what we have to do. How do we actually implement this method? So for step 1, we try to find out any arbitrary initial point x1, and there will be some constant alpha 1. For example, this is 10 to the power 4, because we have to take large number, and then there will be some coefficient c1, which is 0 to 1, strictly 0 to 1, and there will be another constant that we have to consider, c2, which is strictly greater than 1, and there will be one tolerance, so that we can put the stopping condition, and iteration number starts with 1. The first task is to set these initial points. So these are input values, and then so compute this one, the gradient at the xi point. Now test for optimality, whether f of xi, if it is 0 or at least equal to, almost equal to 0, this is another way to say that the norm of this delta f of xi is actually less than some epsilon, for example 0.001. That means this is possible only when what we have said, that norm of this point root over x square plus y square, right? The norm of this in two-dimensional space, if the from 0, 0 to xy point, the distance is okay. So from this one, if we have this condition satisfied, then we stop. Otherwise, we have to proceed next. For optimality, just remember that for optimality, we have to satisfy this equation, that gradient of xi almost equals to 0. This is another way of saying that. Otherwise, we have to go for the next iteration, next step, that is to find xi plus 1. Okay. And this is nothing but J is the Hessian matrix, I is identity matrix. This one is multiplied by the gradient at that point. Okay. So here you can see that we are not using any lambda star. We are not using. We are directly imposing the direction. So thus, after finding this value, we have to find out this f of xi plus 1, And if we verify that this is less than f of xi in the previous step functional value, then we move to the step 6. Step 6 says we have to set this alpha I plus 1. For example, alpha 1 is we have taken 10 to the power 4. Then alpha 2 will be C1. So C1, for example, C1 equals to 1 by 4. Then alpha 2 will be, because C1 is less than 1, greater than 0. So this is will be, so this would be like 2500. So this constant, these coefficients, the alpha coefficients, they are actually defined in this way. But condition is this one. If we are going in the right direction, then we will define this alpha in this form. But if you go in the wrong direction, that means this value, the next step value is actually bigger than the previous step. Then we have to go for of this form. So for C2 greater or equals to 0, greater or equals to 1, strictly greater than 1. For example, C2, maybe it is 1. Okay, C2 equals to 2. Then this alpha I, for example, then alpha 2 will be our 2 times 10 to the power 4. If we go in the wrong direction, then we will apply 7, step 7. If we will go in the right direction, we will apply 6. So this is how we will actually implement this method. Okay. Just like I have said that we may introduce lambda I, but in that case we have to find out the one-dimensional search method, similar to one-dimensional search method. So as a remark, we have said that. Now, if you remember the problem, f of x1 and x2 equals to x1 minus x2 plus 2x1 square plus 2x1 x2 plus x2 whole square. Here, assume x1 0 comma 0. We start with the initial point. Then assume alpha equals to 10 to the power 4. C1 equals to 1 by 4. C2 equals to 2 and epsilon. Stopping condition, the tolerance is 10 to the power minus 2. Or you can say that 1 by 100, 0, 1. Okay. So if we have this condition, then we can stop. That means if delta f of xi is less than 0.01 or less than or equals to, then stop. Otherwise, continue. So what we have to do first task is to find out the gradient f of x1. So this is delta f del x1 del f del x2. So this is nothing but 1 plus 4x1 plus 4x2. then -1 plus 2x1 plus 2x2. So if you substitute delta gradient of f of x1, so this is 0. So 1 plus 0 plus 0 minus 1 plus 0 plus 0. You will get 1 minus 1. Okay. And the Hessian matrix, for example, Hessian. Okay. Remember when Hessian can be, this is just a notation. Sometimes we can write F, sometimes we can write J. But remember the Hessian matrix is H of x. We have said that del 2 F del x1 to del 2 F del x1 del x2 del 2 F del x1 del x2 del 2 F del x2 2. So there we have seen 4 2 2 2. So yeah, it will not change depending on the value of x1. Since this is a constant matrix, so x1 is nothing but it will remain the same. 4 2 2 2. Now we will perform iteration 1. Sorry. Okay. Let us verify this gradient of x1. So here we have to verify after finding this the norm of gradient of f of x1 is actually 1 square plus 1 minus 1 square. So this is 1.4142, which is not less than 0.01. Okay, so we have to proceed. So how do we do that? What we have to find? We have to x1 plus alpha 1 into I. Let us find out. So this is 4, 2, this 2 and 2. Alpha 1, we have assumed 10 to the power 4, or let us write 4 zeros, 1 0 0 1. Okay, so here it is. Now we have to take it inverse. So Hessian of into alpha 1 into I, the inverse. That means we have to take the inverse of okay. So this what will become you can use this 1 minus 1. So x2 will be x1 minus this one h of x1 plus alpha 1 into I inverse. into this one, this gradient of f of x1. So this is nothing but 0, 0. Then we have 1, 0, 0, 4, 2, 2, 1, 0, 0, inverse, and we'll multiply 1 minus 1. So if you just simplify it after finding this inverse, so this will become minus 0.9998 10 to the power minus 4, and this is 1.0000. Let us write down the 4 10 to the power minus 4. Okay, so x2 we have this one. Now the task is to verify whether x2 is optimal point or not. So find out delta f of x2. Okay. So this is nothing but we will try to find out. This is no. Before we go, whether it is optimal or not, we have to check whether we are going in the right direction. So for that f of x2, we need to verify. That means f of x. What was our f of x? x1 minus x2 plus 2x1 square plus 2 times x1 x2 plus x2 square. So this is our x1 now. This is our x2 now. We'll substitute these values here. Okay, and if we calculate, this value will be negative 1.9997 10 to the power minus 4, which is clearly less than 0, which is nothing but the f of x1. Okay, so we are at x2, f of x2 is less than f of x1, so we are going in the right direction. But whether it is optimal or not, we have to verify. Delta of f of x2. That means, if you remember, 1 plus 4x1 plus 4x2 minus 1 plus 2x1 plus 2x2, and then x2 just now we have calculated. Okay. Here it is 0.99, this one. So this x2 will be substituted there and try to find out. So this one will become 0.9998 minus 1.0000. Again, the norm of this f2, f of x2, is actually 1.4141. So this is not less than equals to epsilon, which is 10 to the power minus 2. So we go to iteration 2. Sorry, this is Okay, iteration 1. Okay, let us call it iteration 2. So what we have to do now? First, we have to find out. We already have found this one, f of x2. Then we have to find out the Hessian of x2. It will remain same. 4, 2, 2, 2. Then we have to find out alpha 2. Because we are going in the right direction, so alpha 2 will be c1 into alpha 1. c1 alpha 1. So c1 is 1 by 4 into 10 to the power 4. So this will become 2500. So now we have to calculate this one, h of x2 plus alpha 2 into I. This is nothing but 4222 plus 2500 into 1001. So this will become 2504. This is 2502. Okay. Now we have to take the inverse of it and then multiply with this f of x2. Okay. So x3 will be x2 minus Hessian matrix of plus alpha 2 into I2 by inverse, and then there will be multiplied by the gradient at f of x2. So this is nothing but, just now we have seen that 9998 minus 1.000. Okay, so here it is 2504 2502 inverse, and this f of x2, sorry, f of x2, this is a gradient of f of x2, 0.9998, and this one is actually different. X2 we have found, here it is. Minus 0.9998 10 to the power minus 4 1 into, okay. So if you just perform this operation using MATLAB or Excel, so you will get the values as x3 will be minus 4.9958 into 10 to the power minus 3, sorry, minus 3 up to 2. No, this is 4 and 5 into 0.000 into 10 to the power minus 4. Similarly, f of x3, we will try to find out. F of x3 is minus 0.9993 10 to the power minus 4, which is again less than f of x2. So again we are in the right direction, because we have seen that f of x2 is minus 1.9997 10 to the power minus 4. So this is negative. So that is why this is smaller. Now what we have to do, we'll try to find out f of x3, gradient of f of x3. Whatever the value, we'll calculate. Next, we'll try to find out the norm of f of x3. If it is less than epsilon or not. If it is less than epsilon, then we stop, and then if it is not, then we proceed. But in this case, it will be actually not optimal. Okay, so we have to perform some more iterations. I mean, if you try to do it in HAL calculation, you will have to do for the rest of the day. All day you have to do this calculation. So that is why we need Excel or MATLAB help. So I'll so you can, this is task. Remember, we had the optimal point is 1 comma, sorry, minus 1 comma 1.5. Okay. So for this purpose, we have to at least our x I will be very close to this point actually, this x star. If we find this, then we are actually done. We have done our task. Okay. So this method is actually a particular case of non-linear least squares. Okay. So it has this some methods are actually just now we have discussed the Marquardt. Then we have Gauss-Newton method. Okay. Now, what are these actually the least square methods? Okay, because we are discussing this nonlinear method. Okay, how many of you know about this linear least square methods in numerical analysis for data fitting? Have you studied in undergraduate course?
I have not studied, but I have read about it.
Okay, okay.
And,
how about others?
Yeah.
Others can respond.
No, sir.
No.
No, sir.
Okay,
No, sir.
then I have to discuss that linear also then. Okay, otherwise you will not be able to understand the nonlinear part. Okay, so I will discuss this case with an example. Suppose we have a set of data xi yi are given, x1. Okay. Some values are given. Data table are given. Now we have to approximate. This is called actually, this is related to regression analysis also. Data fitting. Find a question is find a curve which passes most maximum number of points. Okay. Now, as you can see that it is if we can try to cover all the points, then we have to. So this is a non-linear case curve, and this is linear curve. Linear. A straight line is a curve which has infinite curvature. Okay. So first we will discuss the linear case. So what we have to do is we'll forget about the non-linear case. So we'll try to draw one line which is very close. It may not cover, it may not pass through all the points, but it can, okay, we can take it. For example, if you think that you are taking the line in this direction, then this is not a good approximation. If you take the line here also, that is also not a good approximation. So you have to take a line in this form so that it is very close to all the points. So these are the errors. Sometimes it is less than, sometimes it is greater than. This is actual value, but we are approximating here. So this is greater than. But the actual value is here, but we are assuming it is here. So that means we are having, sometimes we are actually overestimating, sometimes it is underestimated. Okay. So that is why we have to take the square term. Okay. So this is at x1 point, the actual value is y1, but this one, what we are doing is y1 bar. At this point, we are taking y1 bar. And we'll try to take the square form, because sometimes it is negative, sometimes it is positive. So that is why we are taking the square term. And our aim is to minimize the total error. So if we can actually minimize this error, if we minimize this error, so what will be? This line will be very close to this. Okay. So like I have said that if we draw a line here or there, so this error will be actually bigger and bigger. So we have to select, okay, we have to select our objective in such a way that this line is very close to all the points. If you remember the introductory lecture that we have discussed, there are facility location problem. 4 zones or 4 cities were there. 4 zones were there. We have to, if this is a hospital, then we have to make it from the minimum distance from all the zones. Okay. So similarly, the same task, we have to minimize the distance from all the students. So this error here, what we want to do is we have to minimize the error, so that we are estimating this value with y1, but y1 cap, but the actual value is y1. So there is there is an error. We have to minimize it. by calculus and some other knowledge we will do this. Okay. So this error function will be called as, like I said, that x1 y1. First we will discuss one variable case, then we will go for two variable and other variable. So this is one variable and linear. One variable plus linear case. So one variable plus non-linear. Okay, there are also possible one variable plus non-linear is there, multiple linear. There are also case multivariable plus linear plus all other things. So we'll discuss the first simplest one. Okay, this is the points are given, x1 y1 points are given, and then we define the error function of this form. So these two are unknown parameters, because what is the straight line equation? A straight line equation can be ax plus b or bx plus a, right? So if we can try to find out this a and b, once we have this a and b, then we are through. Then we can say this line is of this form, whether this is line of this form or of this form or of this form. So once we find a and b, then we can find this line, straight line. So that is the aim of this term. So we have to minimize the error with respect to a and b. So for that we will take the partial derivatives and we'll make it 0, the gradient equals to 0. Okay. So if we differentiate this for equation, if we differentiate with respect to a, so this will be 2 times of this form into this negative term is there, so negative xn. Similarly, for with respect to partial derivative with respect to b, we'll have this one. And then because we want to minimize this error, so we have to make them 0. Now what we'll have with this, we will try to substitute this x values. Now this is a, try to, if you just try to separate them, actually just try to write this one on the right hand side and other, just try to separate them, all the values, because our aim is to find a and b. Okay, so these are unknown variables and these other values are given, xn, yn, sorry, xn and yn are given. So we can produce equations. So this is a system of linear equations in a and b. Okay, xn all are given, xn are given, xn, yn also given. So all these values are given. Now what we can do is this form. So these are actually called normal form, to make it simple without explicit this n equals to 1 to n, all of this. This can also be written as of this form in the matrix form, xn, then xn, and then it is also written as xn and r to n, this is n, A to B, and this is xn yn, and then yn of this form. So we can also write in the matrix form also. Okay. Now let us see one example. Then our idea will be clear. So these are the 5 values that are given: x1, x2, x3, x4, and x5. Similarly, y1, y2, y3, and y4 and y5 is given. Now our first task, because note that we have to find summation x square plus summation x plus summation x into y plus summation y. So we write down x value, y value. We'll take this summation, this is 15. We take this summation y, this is 25. We take this x into y, so 1 into 2, this is 2, 2 into 5, this is 10, 3 into 3, 9. In this way, so this becomes 88. And then this x square, okay, this is x square, 2 square equals to 4, 3 square equals to 9. Similarly, we get this to 55. Now, what we have to do? We have to substitute these values here, so that we can get a equation, a system of equation in A and B. Okay. So once we do that, we can find that the values of A equals to 1.1 and B equals to 1.3. So the equation of the linear equation, okay, the line that is going to approximate all the data point, which is nothing but 1.1 plus 1 into 3x. Okay. And if you try to find out that the y and y cap differences, so this is our y cap now. Remember, we are approximating y cap. So if you try to find out, this is y minus y cap, point minus 4, minus 0.4 is there. Okay, so this is overestimating. This is underestimating. Okay. So in this way, you try to sum up. So the sum will be 0. So finally, the resultant that we are getting is actually 0. So error, resultant error is 0. So that is our aim. So this is how we can actually use least number of squares. So why it is called least squares? So because we are actually taking the least possible. So first we are taking the square terms. Now there may be a situation like this. The data can be given in this form, but if you try to approximate with line, it is not going to help us properly. So for that case, a curve, maybe a parabola, is a better approximation. So this linear least squares, this regression is actually not well suited. This is very ill suited. But a parabola can be more preferable for this type of data. So for that, what we have to do? This is more or less a equation of a parabola. An equation of a parabola can be ax square plus bx. Okay. So for that, again we will take the error term will be there, some time error term, and this is y minus all that error, and again we will take the square term only. Okay. So for that, again, we'll try to find out the error equals to 0. Squares of the residuals. So we'll make it 0. Here 3 unknowns are there, A0, A1 and A2. So we'll have a system of linear equation of 3 by 3 matrix we'll have. Okay. And in this way, what we'll do is we'll try to simplify again to find out the normal form. And our aim is to find out these 3 values. For an example, if you think about, so this is a different case actually. Yeah. So if we have of this form, let me just show. Yeah. So this is A0, A1 and A2. This type of case we can find. So from there, if you find out these values, then directly you can get the parabolic equation. Okay. So from here, this y will be the resultant y, the parabola will be the best suitable least square which is best fit to all the data. Now there can be a little complicated situation. Here y is actually f of x1 and x2. One variable y is a function of 2 variables, 2 independent variable, 1 dependent. Earlier we had y equals to f of x. So for this type of cases, we want to use multiple linear regression line. So for this type of regression or least squares, we have to use I equals to 1, 2, dot, 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 no matter how much. For example, number of finite, for example, k different lines we are using. Okay. Since we are using the linear equation, so we are not taking any square forms. So for this type of least square problems, again we'll have a line in 3-dimensional, as you can see that can be written of this form: y equals to in 2-dimension, a line of this form is equals to this. That means this is a surface you try to fix. We are trying to approximate. So this is a becoming curve. Okay. So let me write down this line. Another line we are having, we may have this line. So x1 is 0, x2 is 0. So 0, 0, this point. At 0, 0, y value is 5. Kind of this. 2, 1. So this is x1 equals to 2. 2, 1. It is actually 10. So here maybe somewhere. So this is kind of z equals to f of xy. Type form. These are actually z value. So if we have a little complicated function or data set, then the error function will be defined of this form. Okay. I indicates the number of points. So for each point, what we have to do, if you just take this figure, let me tell you the story about this problem. So I equals to 1, I equals to 1, 0, 0. So at this point, we are actually approximating this value y minus y. Okay. So along this x1 direction, we have I equals to 0 and x2 equals to 0. I equals to 1, x2 equals to 0 in this direction, and all other points actually considered. So this is basically x1, x2, I equals to 1, I equals to 2, and I equals to some k. x1, x2 will be there, and then corresponding to k values will be corresponding to this y values will be there. So in order to approximate, we have to make this. So after making to 0 and simplifying, we'll get this system of linear equation. This is actually multiplied, not equal to, so this equals to this. Okay. So what we have to calculate? See here, 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 quantities, but we can see that there are some similarities. So this one and this one equal, this one and this one are equal, this one and this one are equal. So we have to calculate. This is n is the number of quantities, number of data set. This is 1, 2, 3, 4, 5, and all other 5, and also this right hand side 6, 7, 8. Okay, so here it is 1, 2, 3, 4, 5, 6, 7, 8. So 8 quantities we have to calculate. Okay, so this is, yeah. So once we do that, you can see that y values are calculated. Okay, then x1 values, x2 values, x1 square, at all points, all the points we are calculating. Similarly, x2 squares and other points. Now, if you substitute these values in these equations and solve it, after solving this, we have this one. So, if you try to go back, yeah, this is the linear. As you can see, so here it is 5, 4, minus 3. Okay. So the point that we are having multiple lines, it's actually y cap is actually a0 plus a1 x1 I plus a2 x2 I. Okay. A0 we have found 5. A1 we have found as 4 x1 I plus, and A2 we have found minus 3 x2I. Now this I actually indicates that particular point that we are considering. Okay, so if you consider about this I equals to 1 point, I equals to 1, if I indicates the 0 point, then for this particular value the line will be of this form, and for I equals to 2 the line may be of this form, so there will be multiple lines to approximate the data to find the best fit, okay, least square, so of this form. And the same idea can be extended to m dimensional spaces. So this was a 2-dimensional case, so here we can extend up to, okay, so this is for linear case. Remember, multivariable multi-dimensional case in the non-linear, of course. Sometimes we can also use e power a into e power x, or logarithm function also can be used to approximate the least square. Okay, those are not our actually intention to study. Our intention is to study the Gauss-Newton method, which is actually a non-linear least square, multivariable. Okay, so we'll discuss it in more details in the next class. But as you can see that if you try to find out the best fit data, you may get of this form. So this is one kind of parabola, ax square plus bx plus c kind of parabola. But if you think, if you can assume best fit, as you can see that this is a periodic function, not only periodic, if you think about the sine function, so this can be treated as, so this is also non-linear function, so non-linear least squares. Okay, this can be treated as a non-linear least square, and here also we can think about the non-linear least squares. Yeah, so here it is. If we have a data set of this form, okay, then a non-linear least square can be of this sine function. Okay. Earlier we had seen, here also we can use, for example, this one. Okay. Earlier we have seen that one linear equation is sufficient to approximate them. Okay. But if we consider this non-linear, so which is actually more suitable? So this non-linear least squares we will discuss in the next class in details. Okay. So this function can be, you can see that this function we have taken here y cap is treated as non-linear function, which is in a 3 variable case. A unknown, omega unknown, phi is also unknown. So we'll start from here in the next class. If you have any doubt, you can ask me.
So is there any way to guess the best function that will fit